Hello everyone. For this tutorial video, I'd like to give the precise, literal definition of what a limit is. For finite limits, for limits at positive infinity, and for limits at negative infinity, and finally, for limits that return a value of infinity or negative infinity. If we have function of x defined for every point on an interval around x equals a, except possibly at x equals a itself, then we write the limit as x approaches a of function of x equals L, if for every number epsilon greater than 0, there is some number delta greater than 0 that satisfies absolute value of function of x minus capital L is less than epsilon, and 0 is less than absolute value of x minus a is less than delta. In this case, epsilon means an infinitesimally small vertical change, and delta means an infinitesimally small horizontal change. If this definition does not make sense, we can see what this means graphically. We mark the point A, where x is, and we mark the point capital L, where our function is. We draw an imaginary line toward both axes from the coordinates of the limit point. Then we see value of limit plus epsilon and value of limit minus epsilon both have the same distance from the value of limit, and similarly, value of x plus delta and value of x minus delta have the same distance from x equals a. We can form rectangles from these two definitions and see visually that any x between x plus delta and x minus delta must be closer to the actual limit point than x plus or minus delta, which is what absolute value of x minus a is less than delta means. And similarly, we can see that a function point evaluated at these choices of x will be closer to L than L plus or minus epsilon. So this is what the other statement of the limit means. Absolute value of function minus limit is less than epsilon. There is actually, by this definition, technically an infinite amount of deltas and epsilons we can choose. But when working with this definition of the limit, you do not have to find a numerical value for epsilon or delta, so you do not have to worry too much about this fact. It is also important to remember, just like with the conceptual definition of the limit, that the limit never actually evaluates what the function literally is at that point. It only gives you an estimation. So now that we hopefully understand what the formal definition of the limit is, we can use it to give proof of limits, as in this example. Prove that the limit as x approaches 0 of x squared equals 0. We do this by noticing 0 is our capital L, x squared is our function of x, and 0 is our a point for our limit. We plug this in to the formal definition of the limit. We simplify the minus 0 on both sides, and now we see, with some trickery, we can actually solve for delta in terms of epsilon. By noticing if the absolute value of x squared is less than epsilon, it follows we can take the square root of both sides to get the absolute value of x by itself. And we have absolute value of x, literally, in our definition of delta, so we substitute in square root of epsilon for delta. We test if this guess is actually accurate by basically doing the reverse of what we just did, so squaring both sides, and seeing that x squared must be less than epsilon, what we saw as the first part of our definition. So we've just proven by the literal definition of the limit that the limit as x approaches 0 of x squared must be 0. If instead we are given the limit as x approaches 4 of x squared plus x minus 11 equals 9, we would plug in this function for function of x. We would subtract 9 from both sides to get it in terms of 0, and we substitute in a equals 4 for the right hand side of the definition. We now subtract negative 9 from negative 11 to get negative 20 as our constant term on the left hand side, and we factor our left hand side. And unfortunately, we cannot directly substitute the left hand part of the definition for the right hand part of the definition. Because of the fact we have x plus 5 on the left hand side, which does not fit anywhere on the right hand side. So we will have to add extra steps to handle that. We take an arbitrary value of k which we say the absolute value of x plus 5 is less than. So now the left hand side is less than k times the absolute value of x minus 4. And we see absolute value of x minus 4 must be less than epsilon over k. We will next make the assumption that the absolute distance of x minus 4 is less than 1. And once we remove the absolute value, we have negative 1 is less than x minus 4 is less than 1. And we add 4 to get x by itself in all terms of the inequality, so we have 3 is less than x is less than 5. If we get it in terms of x plus 5, we would add 5 to every part of the inequality, so x plus 5 is in between 8 and 10. In conclusion, the absolute value of x plus 5 must be less than 10, because of the fact 10 is the greater of these distances than 8. And we remember from what we saw earlier, the absolute value of x plus 5 must be less than k. So now we know the exact value for k is 10. In conclusion, absolute value of x minus 4 must be less than epsilon over 10. But also remember, to get these steps, we had to take absolute value of x minus 4 is less than 1. This means that delta must be the minimum value between these two values, to guarantee that it is less than or equal to both of these values at the same time. So now, if delta is less than or equal to epsilon over 10, it follows the absolute value of x minus 4 must be less than epsilon over 10. By similar reasoning from what we found for delta, we know that absolute value of x minus 4 must be less than 1, so the absolute value of x plus 5 must be less than 10, by the laws of arithmetic and algebra. So now we are ready to test if our original function gives us epsilon with these values specified. We do this by taking the original function as it literally appeared, then doing the subtraction to combine the constants, then factoring, then seeing because absolute value of x plus 5 is less than 10, the overall function must be less than 10 times absolute value of x minus 4, and we substitute in epsilon over 10 for the absolute value of x minus 4 part, and 10 times epsilon divided by 10 is simply epsilon. So we have proven that our values for delta work and give us the original function less than epsilon as defined in the beginning of the limit. In conclusion, the limit must be 9 because we have proven it using the formal definition of the limit. We can state that a limit gives positive infinity if the function of x is greater than any arbitrary value m, whenever the absolute value of x minus delta is in between 0 and delta. And similarly, the limit is negative infinity if the function of x is less than any arbitrary value negative n for this range of x values. An example of a specific function is limit as x approaches 0 of 1 over x squared equals infinity. We see that 1 over x squared must be greater than any arbitrary value m whenever absolute value of x minus delta is in between 0 and delta. We can actually solve for x in terms of the m value by first noticing 1 over x squared is greater than m. X squared must be lesser than 1 over m by algebraic rearranging. So the absolute value of x must be less than 1 over the square root of m. So in conclusion, it looks like delta is 1 over the square root of m. We test if this works by first squaring both sides, then flipping the equation back to get m by itself. And we see that our choice of delta gives the original limit, which was 1 over x squared is greater than any arbitrary value m. Hence, we have proven by the definition of the positively infinite limit that the limit as x approaches 0 of 1 over x squared is positive infinity. Lastly, we can formally state the limit at x equals positive or negative infinity as, for positive infinity, the absolute value of function minus limit must be less than epsilon, whenever x is greater than any arbitrary value m. And for x equals negative infinity, it is x is less than any arbitrary value n, although the epsilon part remains the same. We can see, if we take the limit as x approaches negative infinity of 1 over x equals 0, that 1 over x is our function, 0 is our limit. We plug this in, we get 1 over absolute value of x is less than epsilon, whenever x is less than any arbitrary value n. We see, because 1 over absolute value of x is less than epsilon, the absolute value of x by itself is greater than 1 over epsilon. We can see we choose n equals negative 1 over epsilon, the negative part being important because in our rearranging of epsilon we have a greater than, but in the original limit definition we have a less than, so we have to make our value negative to flip the sign. We can confirm this is true by first taking x is less than negative 1 over epsilon, taking the absolute value of both sides, which will flip the statement, stating that the absolute value of negative 1 over epsilon is simply 1 over epsilon, isolating epsilon by itself, then finally rewriting it so that it is exactly like the original limit, by rewriting 1 over absolute value of x as absolute value of 1 over x, and then subtracting 0 within the absolute value. Because this matches exactly what the original limit was, we have proved concretely that the limit as x approaches negative infinity of 1 over x must be 0. One final thing we can do is give a very formal definition of continuity by stating the absolute value of function of x minus function at point A is less than epsilon, whenever 0 is less than the absolute value of x minus a is less than the absolute value of delta, as we assumed with continuity that the function at point A is exactly equal to the limit at that point. So therefore, we plug in function of a for capital L in our definition of the limit. Now that we have covered a few problems relating to the actual definition of the limit, I will leave it as an exercise for a student/viewer to prove the limit properties we found earlier in a rigorous fashion. And I will also transition away from limits and toward the study of derivatives, which are the rate of change of a function at an infinitesimally small point. Don't forget to subscribe if you found this video informative, and make sure to see the other tutorial videos, and follow me on either Facebook or Twitter for more content.